Okay, if Taylor and Maclaurin series are the hardest topic in BC calculus, Lagrange error bounding is the hardest topic within um, the Taylor and Maclaurin chapter. All right, so what is Lagrange error bounding? All right. So we've seen how to use a partial sum of an alternating series to estimate the series. And you know that you're good till the next term in the alternating series. The problem comes in is when the series is not alternating, how can you bound the error? How can you know how close you are? Now, if you have a Taylor series, then you can do this. Okay, so we're going to say I have the kth partial sum of the Taylor series. So this is going to go from n equals 0 to k of the nth derivative at a over n factorial times, that fraction bar is really big, all right, over n factorial times x. I can draw an x minus a to the nth. Okay, so this is the kth partial sum. What I want is that if f of x is this series when I go to infinity, right? So that means I'm on the interval of convergence. Then how close is the kth partial sum at x? All right, and this is where we get this weird formula. This thing is going to be bound above by. All right, so this shouldn't surprise us. The n plus 1 factorial would be just as though we are in the next term. And then we're like, my absolute value of x minus a to the n plus 1. Again, no, straight absolute value, there we go, to the n plus 1 is also just like we're in the next term. And it would just be great if this was like the n plus first derivative of a. And it's really close. It's the n plus first derivative at some value c, where we're going to take the absolute value of this thing. We're going to take the maximum value of c on the maximum value of this derivative when c is on the interval from a to x. Okay, so like that's really crazy. Okay, so it's not just enough to take the next term. You actually have to maximize the interval and maximize the n plus first derivative on the interval between whatever this x value is and wherever this thing centers. Okay, that got crazy there for a second. So it's wherever this thing centers, whatever that a value is. So I'm going to look at the interval. Okay, so this is an interval from wherever a is to wherever x is, right? And then I'm going to look at this f to the n plus 1 of x, and I'm going to pick that maximum value, and I'm going to call that c. Now, once I have that, that's my numerator here. I'm going to put that over the n plus 1 factorial, multiply that by x minus a to the n plus 1, and I have the upper bound for the error between the function and the kth partial sum. All right. Now, this means that they have to give us a pathway for finding the maximum of that n plus first derivative on the interval from the center of the series to the x value that we're evaluating f at. There has to be a way in all of these problems to find that maximum. We're going to look at a problem now, and we're going to just kind of walk it through and see how this plays out. Okay, we are going to use a Taylor series to try to approximate the cube root of 9. Okay, so this is what we're going to do. We're going to let f of x be the cube root of x. We're going to build the Taylor series centered when x is 8, right? So remember, in our framework, this is the a, right? So I'm going to do this, and I'm going to do this with the second degree Taylor polynomial. All right, so I need f of x is the third root of x, which is also x to the 1/3 power. F prime of x is going to be 1/3 times x to the negative 2/3. F double prime of x, well, let's see, negative 2/3 times a third is negative 2/9. X to the, let's see, 2/3 minus 3, there's this negative 5/3. Okay, so if I'm centering at 8, f of 8 is the third root of 8, right? The third root of 8 comes up as 2. All right, so f prime of 8, let's see, this is 1/3 times 8 to the negative 2/3, right? So let's see, the third root of 8 is 2. 2 squared is 4. The negative puts it in the denominator. So this comes up as 1/12. Okay, fantastic. And f double prime of 8, well, let's see. That's negative 2/9 times 8 to the negative 5/3. Third root of 8 is 2. 2 times 2 to the 5th is 32. Put that at the bottom. Let's see. The 2 and the 32 are going to cancel, making negative 1/16 times 9. 16 times 9. Let's see. 16 times 9 is 144. So this is negative 1/144. Okay. So we have what we need to make the second degree Taylor polynomial. So the polynomial second degree of x is f at 8, which is 2, plus f prime at 8, so that's 1/12 times x, minus f double prime of 8, well, it's going to be plus negative 1/44 divided by 2 is 1/288, and then that's x squared. Now, here's the thing. Oh, sorry, this is centered at 8. So let's fix that. This is not centered at 0. This is not Maclaurin. So this is going to be x minus 8 minus 1/288 x minus 8 squared. And that's a good thing that I caught that, because if I want this valued at 9, because we're trying to find the cube root of 9, and this is 2, and 9 minus 8 happens to be 1, so this is going to be plus 1/12 minus 120, or 1 over 288, is this also becomes 1. Aha, that makes it nice. All right, so 2 plus a 12th minus 1 over 288. All right, so I'm going to let you take that with your calculator. That actually works out to be 599 over 288, which is approximately 2.07986, give or take a little bit. Okay. So this is my estimate for the cube root of 9. Now the question is like, how good is that estimate? Like, how well did we do? And without actually taking the cube root of 9, because I don't have a method for doing that, there has to be a way to check this. So this is where my Lagrange error formula comes in. Okay, so we know that the difference between the cube root of 9 and 599 over 288 has to be less than or equal to, all right, the maximum of when C is on the interval from, well, let's see, A we know. A is 8. And the X value here is 9, the maximum on the interval from 8 to 9, of F triple prime of C, right? And I'm going to take the absolute value of that, right? So it's going to be that over, let's see, N was 2, so this is N plus 1, so that's going to be over 3 factorial times the absolute value. Well, let's see, that's going to be X, which is 9, minus A, which is 8, to the third. Okay, so this is what remains to be known, right? But if you do some examination here, you can figure out what the third derivative is. We had that the second derivative at x was negative 2/9 times x to the negative 5/3, right? So this means that the third derivative of x is going to be positive 10 over 27 x to the negative, let's see, 5/3 plus 3, so that's going to be 8/3. Negative 8/3. Okay, so if you look at this thing is always positive on the interval. So on the interval from 8 to 9, this thing's always positive. And in fact, it's always decreasing, right? So this thing is going downward. You can like pop that thing in a calculator and you can see on the interval from 8 to 9, this guy is decreasing, decreasing, decreasing. So if this thing is always decreasing, the maximum for C on the interval from 8 to 9 of F double prime of C has to occur at 8. Why does it have to occur at 8? Because it's decreasing. So everything to the right of 8 is actually going to be, so this has to be F triple prime of 8. If you take F triple prime of 8, that's like 10 over 27 times 8 to the negative 8/3, right? All right, so let's put this all together. Okay, so we now know that the third root of 9 minus 599 over 288 absolute value has to be less than or equal to 10 over 27, 8 to the negative 8 over 3, divide by 3 factorial times the quantity 9 minus 8, which is just 1 to the third, which this thing is, well, we're not going to get a fraction out of it, but this thing is approximately 0.000241. That's really kind of cool. I mean, that means I've got like almost 4 decimal places, at least 3 decimal places of accuracy with only 3 terms from this Taylor polynomial, right? So with only 3 terms, I have 3 decimal places of accuracy. So let's check and make sure that that's actually correct, okay? All right, so I'm going to pull out my handy-dandy calculator here, right? And I'm going to say, okay, it's second, nope, not second, I want math. Math, number 4 is the third root of 9. And it tells me that that's around like 2.08. And then I take this other number, 599 divided by 288, right? And that's like 2.0798. So these things look really, really close, right? But the argument is that these things should be like 3 decimal points close. So let's see. If I actually take the absolute value, right? So math number 1, the absolute value of the cube root of 9, and I subtract the quantity, what do we got? 599 divided by 288. So that's my error. This gives me 2.227119,408 times 10 to the negative 4th. So that's 0.00022, whereas my error bound said that I had to be less than 0.002411. So yes, my error is within 3 decimal places of everything here. So there you have it. An example of Lagrange error bound from beginning to end, and possibly a way to compute the cube root of 9 without actually having a calculator handy, or at least getting close enough to it for most intensive purposes. All right, so this works even though the series may not be alternating, and so there's an example. I'd suggest, like, kind of walking through this more than once to kind of see all the moving parts of it. And then we're going to look at the next couple of classes some problems that deal with this exact topic, specifically one that came up in 2008, which was an awesome problem and one that many, many people missed when it came up on the BC exam. So there you go.